In a previous video, we showed that the differential equation for Newtonian orbits can be expressed in the following form. The second derivative of u with respect to theta plus u is a constant. It's Newton's constant times the mass of the gravitating object divided by the square of the angular momentum per unit mass. The gm over h squared is a constant. In the theory of differential equations, this is an easy equation to solve. All you have to do is to find one particular solution, which in this case will just be gm over h squared. Add to this the general solution of the homogeneous equation, and you'll have the general solution to the original equation. This last differential equation is well known. Its solution can be expressed in closed form. U, for the homogeneous equation, is going to be a linear combination of cosine theta and sine of theta. Here, the a and the b are constants. Adding this to the particular solution that we previously stated, we get, if you take the second derivative of this last expression, add in the last expression, you'll get the constant gm over h squared. So this is, in fact, the general solution of our equation. The a and the b are constants, which could be determined if we knew some more things about our solution, or we can use them to simplify our situation. If you look at the derivative of u with respect to theta, you get the derivative of u with respect to theta is negative a sine theta plus b times cosine theta. Suppose I arrange my graph so that the minimum or maximum value of u happens at theta equals 0. Then it would have to be true that b will have to be 0. My u solution then is only going to have the part that has the a in it. The second derivative of u, looking at both the first and second derivatives, if we choose the a to be positive, then at theta equals 0, the first derivative of u is 0. The second derivative will be negative a, which will be negative. We will have a maximum value for u, and since u is the reciprocal of r, this choice of coordinate system setup will put the closest point to the origin on our orbit on the positive x-axis, where theta is 0. In our u solution, factor I'm going to make up a name for the constant a times h squared over gm. I'm going to call it e. Since u and r are reciprocals of each other, I can write that last formula in terms of r, and then using properties of fractions, and calling the constant upstairs capital F as we have done before. In the case where the eccentricity is between 0 and 1, we have already seen that this last formula is the equation of an ellipse with one focus at the origin. The question of what this means when the eccentricity is not less than 1, we'll look at later. But for now, this completes the three pieces that I wanted to look at for the ellipse. This shows, starting from basic physical principles, that Newton's law of gravitation predicts the orbits of the planets are ellipses, with the sun at one focus. Coming soon, the hyperbola.